In this final section of Chapter 8, which also happens to be the last section of our entire course, we're going to focus on hypothesis tests, where we're testing a claim about a population mean. Testing claims about population means is one of the most important skills that you can acquire in this course. In this section, we're going to focus primarily on problems where the population standard deviation sigma is not known, and we'll explain why the emphasis is on these kinds of problems. It happens to be the more realistic case. But we'll also have a very brief discussion on procedures used when sigma is somehow magically known, which is rare, and there are some big assumptions made for those problems. So let's talk about why it is more realistic for sigma to not be known if we are making a claim about a population mean mu. It's because if we're testing a claim about mu, that means we don't know mu's true value. After all, if we know the value of mu, why test a claim about it? It either is equal to mu or it's not. There's no need for a hypothesis test. However, sigma, which is the population standard deviation, is calculated directly from mu. So if mu is not known, then there can't possibly be knowledge about the value of sigma, which is calculated directly from mu. So it is more realistic for sigma, the population standard deviation, to not be known if mu is not known. If we do encounter a problem where there is a value of sigma provided, that means that they're either using a historical value or they're making an assumption about what sigma stands for, but it is not realistic. However, we are going to talk about how to handle those problems where sigma is magically known. However, we'll emphasize problems where sigma is not known. Let's review some notation quickly. Lowercase n, as always, stands for the sample size. X bar is going to continue representing the sample mean. S is going to continue representing the standard deviation for the sample. So S is sample standard deviation. Mu with an X bar subscript, or just mu without any subscript, will stand for the population mean. There are some requirements for these methods. First of all, our sample needs to be reliable, it needs to be good. Therefore, it needs to be a simple random sample. Second requirement is that either the original population is normally distributed or we compensate by having a large enough sample of over 30. In this course, our problems will, for the most part, satisfy these requirements because we want you to practice with the method. But in the real world, of course, it would not be appropriate to use these methods if the requirements are not met. The test statistic for testing claims about a population mean where sigma is unknown, where the population standard deviation is not known, is a t-statistic. And the formula for calculating this test statistic is as follows. It will be the sample mean x bar minus the claimed value of mu, the claimed value of the population mean, which appears in your hypotheses, divided by your standard error, where the standard error is the sample standard deviation divided by the square root of the sample size. We're going to look at two ways of making decisions at the end of these hypothesis tests. Either we can calculate a p-value and compare it to the significance level alpha for the test, or we'll use critical values to find the critical regions. I will say that p-values when it comes to t-distributions should be calculated using your calculator only, because the t-distribution table will not give you precise t-values, only ranges, so it makes it a little bit less straightforward and a little bit more confusing. On your TI-83 and 84 calculators, you can go to Stat, Tests, and then the t-test. Unfortunately, the TI-36X Pro does not have this command. However, any of you can use the critical value or the critical region method, regardless of whether you have a calculator or not. And we will be using table A3, which is the t-distribution table. And recall that to use that table, you need to refer to the degrees of freedom, which is always one less than the sample size. A few reminders about the t-distribution, which we were introduced to in Chapter 7. First of all, there is a different t-distribution for each different sample size. So whereas there is one standard normal curve, one distribution of z-scores for all problems, there are different t-distributions depending on your sample size. And each t-distribution corresponds to one row in Table A3. Also, the t-distribution has the same general bell shape as the standard normal curve. However, its wider shape reflects the greater spread or variability that is expected when we use the sample standard deviation versus the true population standard deviation. So S is an estimate for sigma. Just as with the standard normal distribution, the mean of any t-distribution is 0, and the standard deviation, however, is greater than 1, and it is going to vary depending on the sample size. However, the larger the sample gets, the more the t-distribution will resemble the standard normal distribution. So the t-distributions get less and less wide and more like the standard normal curve as the sample size increases. Let's go through one full example through these slides, and then as I did with the previous section, I'm going to attach my write-up for this hypothesis test in a more concise way, but we'll go through the details in the following slides. The author obtained times of sleep for randomly selected adult subjects included in the National Health and Nutrition Examination Study, and those times in hours are listed below. Here are the unrounded statistics for this sample. So we have 12 sample data points. The mean of the sample is 6.83 hours. The standard deviation for the sample, S, is about 1.99 hours. A common recommendation is that adults should sleep between 7 and 9 hours each night. We are asked to use the p-value method with a 5% significance level to test the claim that the mean amount of sleep for adults is less than 7 hours. Let's unpack a lot of what I just read through. First of all, they're asking us to use the p-value method, which we will, and we'll demonstrate how to use that on the calculator, but I will also go through the critical region or the critical value method as well. Because we are working with sample standard deviation and not the population standard deviation, we are in the more realistic scenario that we will have to use the t-distribution that corresponds to the appropriate sample size. The claim here is that the mean amount of sleep for adults is less than 7 hours. There's a clear direction here that will indicate how we're going to put together that alternative hypothesis. Here are the 12 original data points. So this is our sample data, and we have already calculated the sample mean and the sample standard deviation. If we had not been given those summary statistics, of course, you can enter these 12 values into your list editor in your calculator and then run the one variable statistics to produce X bar and S. A quick requirement check: although our sample size is small and although we don't know whether the original population is normal or not, we're going to go ahead and assume that the original population is normally distributed. Otherwise, we wouldn't be able to perform this hypothesis test. The claim that the mean amount of adult sleep is less than 7 hours becomes mu less than 7. That is going to be a statement of inequality, so that becomes the alternative hypothesis. The null hypothesis is always a statement of equality, so we will state that mu is equal to 7 hours. Because of the direction of that alternative hypothesis, this is going to be a one-tailed test, specifically a left-tailed test. We are to use a significance level equal to 0.05. That's going to be alpha for us. And because sigma, the population standard deviation, is not known, and instead we're using the sample standard deviation S, we will proceed by using the t-distribution. Here's how we're going to calculate our test statistic. We have x bar as 6.83 repeating, minus the claimed value of mu, which is 7 hours, divided by our standard error, which will be our standard deviation from the sample, divided by the square root of the sample size 12. So we get a test statistic of negative 0.29. That will be just slightly to the left of the center, just slightly to the left of 0. If we were to use the TI-83 or 84 calculator, we would be able to find a more precise p-value. Notice that on your calculator, what they refer to as a lowercase p is actually the p-value. And I know that's kind of confusing because we are letting lowercase p stand for the unknown population proportion when we're working with proportion problems. But on the calculator, the lowercase letter p refers to p-value. So the p-value is approximately 0.3887, which is quite large. We were kind of hoping it would be less than 0.05. But because it is large, then we failed to reject the null hypothesis. The p-value was greater than the significance level, and that leads us to reject the null hypothesis. The interpretation is that because we have a large p-value, we conclude that there is not sufficient evidence to support the claim that the mean amount is less than 7 hours. I prefer to say that we do not have sufficient evidence against the claim that it is 7 hours. I always like to write the conclusion in terms of the null hypothesis. Now, for those of us who don't have the TI-83 or 84 calculators, or we simply choose not to use it, we're going to reach the same conclusion by using the critical value or the critical region method. Recall that this is a left tail test. Our test statistic value is negative 0.29. Sample size is 12, so the degrees of freedom is 1 less than that, or 11. Using the table for the t-distribution, table A3, if we find the row for 11 degrees of freedom, and then we pair that up with the column that has a one-tailed area of 0.05, we find that the corresponding t critical value is 1.796. Now remember, the t-distribution table only gives us positive values. We are in the left tail, which means that we're going to use the negative counterpart of negative 1.796 as the correct critical value. Here is table A3 with the t-distributions. Again, we have a sample size of 12, so we're going to use 11 degrees of freedom. Here is a row for 11 degrees of freedom. In this row, we're going to match that up with the area in one tail equal to 0.05. So this is always going to be where we look up our significance level. One-tailed test, 0.05 area in one tail. Go down to the row for 11 degrees of freedom, and here we find that critical value of 1.796. Again, all of these critical values on the table are positive, so if you're using a right tail test, this is exactly what you use, but if you're using a left tail test, you're going to have to use the negative critical value. So just place a negative sign in front of whatever you look up here. Now let's look at the sketch of this t-distribution. Here is our critical value, negative 1.796. Look at the area in that left tail equal to our significance level, 0.05. This is the critical region. If our test statistic fell in the critical region, we would conclude that we have sufficient evidence against the null hypothesis. We would reject the null hypothesis. However, in this case, our test statistic, negative 0.29, does not fall in the critical region. Therefore, we fail to reject the null hypothesis. So the conclusion is the same as using the p-value method. Now let's look at the less realistic scenario where we're testing a claim about mu and somehow sigma is magically known. Remember, this is a less common scenario because we're making some lofty assumptions. If we don't know the true value of mu, there can't possibly be a way for us to know the true value of sigma, since sigma is calculated from mu. However, let's assume that sigma is somehow magically known. It's provided either through historical information or just by assumption. The requirement for us to conduct the appropriate test is very similar to what we saw previously. We still need a simple random sample, which is the strongest sampling technique. The population standard deviation, sigma, somehow has to be magically known and provided. And if we don't know whether the original population is normally distributed or not, then we need to compensate by having a large enough sample of greater than 30. In the event that sigma is magically known and we're testing a claim about the mean, then we use a z-score, which is kind of back to our comfort zone. Our z statistic is calculated as follows. It's the sample mean x bar minus the claimed value of mu, the population mean, divided by the standard error, which is the population standard deviation sigma divided by the square root of the sample size. This is the only difference in the procedure, other than p-values can be obtained through your TI-83 or 84 calculators, but I think by now most of us are comfortable using table A2 with those negative and positive z-scores. Critical values in the critical region can be found using table A2. So the remainder of the test is going to look very similar to what we did in section 8.2, where we were testing a claim about a population proportion, because all of those problems used z-scores. So really the only difference is that we're calculating z in this manner, but the remainder of the test is going to follow the same techniques as we use for section 8.2.